Okay, we can get started now. Just looking through the feedback from yesterday, it seemed like probability was the biggest pain point. So, thought we would go through a bit more of a review, especially MLE. Can I just get a show of hands, who's still confused about MLE or MAP? Okay, a lot of people, a lot of people, yeah. Okay, so just a refresher on what MLE is. Oh, by the way, have you looked at MLE before? Okay. Yeah. So MLE, or maximum likelihood estimation, is once we've worked out our distribution that the data belongs to, we want to work out what parameters are best suited to model that data. And one of the methods that we use to do that is called MLE. And it works around the approach of maximizing the likelihood that of our data given the parameters. So essentially, we just keep changing the parameters and try to increase the likelihood of the data. And then one of the questions that we had yesterday was how do we know our distribution in the first place? So MLE does assume that you already know the distribution, or at least it assumes that you've made a hypothesis of what distribution your data belongs to. And then if you didn't know in the real world how they find out the distribution, you need to do visualization or summary statistics or other tools that we won't cover here, but we're just focusing on the part where we already have our distribution. And then Deepak also asked yesterday, what happens if we already know our distribution, can't we just solve for the parameters, for the mean or for the standard deviation? So yes, you can do that, especially for Gaussian data, so normally distributed data. You can just calculate the mean, but you can't always do this for every distribution. And so that's why we have a tool like MLE, which is sort of a standard approach for whatever distribution your data belongs to. And yes, if you run MLE on Gaussian data, you will just get the standard, the sample mean. So you could have just calculated the mean. So these are called unbiased estimators. Yeah. Does anyone have any questions on this part?
When you say some distributions are more complex, what do you mean? What's a mixture distribution?
So there's a mixture Gaussian distribution, which is two or more. Yeah, sort of Gaussian curves in one graph.
So Emily can account for that.
Yeah.
Oh, cool.
Yeah. And then how do we work out our likelihood function? So this is one of the first steps for MLE. So this is completely dependent on your distribution, right? And you just need to know the PDF or the PMF, and you would know this just based on the distribution of your data. So this very useful ChatGPT generated graph has all the likelihood functions for whatever distribution you're looking at. Yeah, it's nothing that you need to memorize, but it's more you just need to know where to find it if you were doing it. And then you can also apply MLE to logistic regression or linear regression, and they would have their own sort of likelihood functions. So you can just, if you were tasked with that, you just search it up and find it. And then I thought we'd go through a bit of a walkthrough of how we would this process would actually work. So this is our this is the PDF for one normal a normal distribution, right? And then essentially how it works is whatever x value you plug in, you're gonna get out a probability that distribution hits that x, right? And that's completely dependent on the parameters that you put in, and the parameters are your mean and your standard deviation. So does everyone know where this came from? Where we got this, how we got to this step?
That was from selecting the Gaussian distribution.
Yeah, so now that if we think our data is normally distributed, this is the function that we'll select. Yeah. Do you have any questions?
Question. So
Yeah.
I thought that was equal to a probability density.
Yeah, probability density, yeah.
Do we need to manipulate that in a way to get the actual probability, or are we just assuming probability density is proportional to the actual probability?
Oh, actually, that's true. If it's a probability density. Yeah, for a single point, you wouldn't get a. Yeah, that's true. Actually, I'm not sure how that works. I'm not sure how that works. But for the example that I'll use like in this thing, like all the other like properties and steps work. Yeah.
Did you put selected from the previous table?
Yeah. So once we know that our data is distributed normally, then we'll just select this. Yeah. So this is just pulled onto the next slide. Yeah. I'll look into that afterwards, and then we can talk about it. But once we have this PDF, then this is how it would look when you do like the next, like you work out the likelihood function. So we just took this for a single data point, and we sum it. So for all of our data, like we sum it to get like the overall cumulative sort of likelihood. So this would be our likelihood function. And then we're going to move on to the next step of making it into a log likelihood function. And the reason why we do logs in the first place is that they're easier to compute, and you're less likely to run into errors when you get into really low sort of float numbers. So this is like a lot of like, this can be like quite complex maths, but can everyone see like how we go from each step? Or is there any like step that's not sort of clear?
Wait, sorry. Like just a question, maybe like a bit before as well. So
Yeah.
Is this the likelihood function, and like so is the PDF part of the likelihood function? As in.
Yeah.
Yeah. So it's almost like you use the PDF to like make the likelihood function. Right?
Yes, that's right.
Okay.
So this top line is sort of like a general formula for a likelihood function. So it's just the sum of, and then your PDF. So you stuck your PDF in, and then this is it just after you've substituted it in.
And like, how do you interpret that? Is it when you're that's multiplication, right? Not-
Yeah, that's multiplication.
So you're like multiplying together all of the possible probabilities of all of the points in the PDF.
No, so it's not all the points on the PDF, but it's all the points of your data. So all of those data points, you stuck it into the PDF. So each of them has yielded a different value, and then you've summed them all together.
So what's the interpretation of that value that comes out?
That
Each one?
of each one is sort of just like likelihood. We just say,
Likelihood meaning,
yeah.
is that same as probability or something else?
I guess it is the same.
Mm.
Yeah, I guess it is the same. But once you sum them, or at least once you take the log of it, it's no longer sort of like you can't just like interpret it as this is the probability that yields all of. Yeah. I believe so. I don't know. I'm not like fully across this topic as well. It's pretty confusing. But maybe once Kwa comes on Thursday, could also ask him some questions. Yeah. I was speaking to him about this yesterday actually, and he said like it's probably like you don't need to know in too much detail, more of just like an intuitive sense, since like he also like, although he studied like many times, like you don't need to be able to work it out by hand. Yeah. Yeah, so we move from just our likelihood function into our log likelihood function. We just log everything. And the reason why, like we also had a question yesterday, why like once you log it, it turns into like a summation rather than product. So I'll cover that in the next one as well. Does anyone have any other questions to this slide first? Nope, okay. So this is how you turn it into a log likelihood function, right? You just log this whole thing, and then that's equivalent to moving the log into the product notation. And then the product notation becomes a sum notation. The reason why this happens is because of our log law here. Yeah. So this is essentially saying log of all of these PDFs sort of multiplying together. And that's exactly the same as just the log of one of them plus the log of another plus the log of another. Yep. Okay, seeing nods. And then I said like, why do we want to do that in the first place? Like, it's because it makes it easier to compute, and you don't get like really, really small numbers where like you start to lose sort of some of the accuracy. And then also another question on what's the difference between a loss function and a likelihood function. So when I was talking about gradient descent a bit later yesterday, we were talking about how we want to minimize our loss. So we have our loss landscape, and we're sort of moving down, trying to find one of those minima. This is the difference between what we just calculated, so that loss function and a likelihood function, sorry, and a loss function. So for a loss function, this is the difference between your predicted value and the ground truth during your training. And once you calculate this, you want to try and minimize it, right? And whereas for our likelihood function, this is how we calculated our likelihood function. And this is something that we want to maximize instead. But you could easily just convert like a log likelihood function into a loss function by taking its negative. Yeah. Any questions on this one?
How do you try and maximize the likelihood function?
Yeah, how do you maximize it? So that's using argmax, which I'll explain, I think, after this. Yeah. So argmax here, it's basically the way that we notate changing whatever variable is down here. So this is just our parameters to maximize the function that is given. The actual method of how we do this would be something like gradient descent. So that's something that would be covered by Qua on Thursday. But yeah, this is how we notate it. So this is to mean that we want to maximize this by changing this. Yeah. Okay. And then for MLE versus MAP, so MLE is the most like preferred and like standard tool. Qua just wants you guys to be able to like know what MAP is in case there's like a paradigm shift or something where it becomes like the more preferred tool. But for MLE, it's essentially two different approaches to the same problem, which is parameter estimation. And MLE does this by trying to maximize the likelihood of the data given the parameters. Whereas MAP takes it the other way around, so they try to maximize the likelihood of the parameters given your data. Yeah, and it's a bit confusing like when you say it out, but when you look at the maths notation, it becomes a bit more clear. So you can see it's just the swapping of this conditional here. Yep. Okay, and this is just a bit of a summary as well on like when MAP may be more preferred than MLE. Because MAP in general, like it's a bit more complex to run and you need to have like some prior knowledge to run it as well. So there are issues where it could be seen as more subjective than MLE. So that's why MLE would be more preferred generally. But MAP is able to work for smaller data sets. And let's say you do have that prior knowledge and you want to put it into your calculation, then MAP might be your tool of choice. Okay. And this is just a brief look at MAP. Like there's nothing here to memorize, but just so you have like a bird's eye view of it. So this is our original Bayes theorem, which we've already seen. And this is what I described MAP to be. So it's the likelihood of the parameters given the data. We can expand it out using this formula. So now this conditional swaps up here. So you have data given parameters. Then you have your PB, which is the prior belief of the parameters. And then you have this bottom term. So just the probability of the data. And then once you have this expanded form, then you convert that to the log likelihood function. So you just logged it. This looks completely different, but if you just log this and then simplify it out, this is what it looks like. Does any other questions on that? Yeah.
How do you estimate the prior belief?
How do you work out the prior belief? Yeah, you would need to, that's like something that like you would have studied your data before and then have a random idea. But like the actual prior belief would like belong to a different distribution. So you'd have to you would incorporate a different distribution and that would represent your beliefs on what the likelihood of the parameters are before. But that's like something that we won't cover. Yeah. So for each, let's say for each like distribution of your data. So let's say I know that my data is normally distributed. There will be a sort of parent distribution that I must use to model my parameters if I want to use MAP. So for every sort of distribution that we have chosen for our data, there will be like sort of like an obvious choice for another distribution that we want to use to model this. Yeah, but that's something that you would have studied before choosing to use MAP. Any other questions? Okay. We'll hopefully get to take a look at this a bit more during the course. So if you're not completely like comfortable with it, that's fine. And we'll sort of like get there in the end. Yeah. I think the course reader and the questions, no, and the YouTube video that I sent in the Discord as well. Those are useful if you have the time. Yeah. But now we'll move on to the focus of today's morning session, which is object-oriented programming. Can someone, can we just get a show of hands if you're sort of like comfortable with this topic and you're pretty like confident with it? Anyone? No? Okay. Does anyone sort of like know the basics of it, but like you haven't had too much practice? Yeah. Okay, that's good. And who like doesn't know what this is at all? Okay, okay. So I guess like since it's a lot of new people, okay, I'll try to like introduce this topic with an analogy. So imagine that you're like a movie director and you're working on like a new exciting film, right? Your film, you want to feature like a range of characters and you want each of them to have like their own personal like unique traits and their own unique like abilities and things like that, right? And each of those characters, they will belong to some category. So some of them like heroes, some of them are villains, and all of them sort of like interact with each other, things like that. And you also want to sort of like do a bit of a crossover and you want to pull some characters from another universe. So from like the Marvel universe, and they sort of make appearance in your movie and they interact with your characters as well. So this is like sort of the scene that I'm setting up. And using OOP or object-oriented programming, you sort of like become that director, right? So this is all of the sort of basic components of OOP. It's like really a paradigm where you write these classes, which are essentially blueprints. So that's, for example, your categories, such as a hero or a villain, right? And there are objects, which are your characters. Your characters belong to one of these classes. So they take on those blueprint traits of your class. Each of your objects, they have attributes and they have methods. So the attributes are sort of like the personality, the traits of your character, and the methods are the actions or the abilities that your characters have. And then libraries are sort of just like things that other people have written. So these are packages that other people have written that you can import into your own code, so you can use all of that functionality for yourself. And you don't have to write it all yourself as well. So hope that analogy sort of got across. So we'll take a look at a more like technical view of it now. So what are the benefits of OOP? So using all of this sort of, using this paradigm, there's the benefit that your code is reusable because you can export it into a library and then have that used like by other people or used by yourself in other in other projects. It also keeps things a bit more modularized, a bit more organized, so you sort of know where everything is and it's just a bit easier to manage. It's also good for flexibility and good for collaboration. So collaboration, and again, once you've exported or a library or you're able to import your friend's library, like you're able to use all of that code in different projects, essentially. So this is, a more technical like sort of view of what the classes and objects are. So for some class, that's a user-defined type, so it's a blueprint. The object is an instance of that class, and attributes are sort of the variables that are tied to that object, where the methods are functions that are tied to that specific object or class. So they must be called along with one of those objects. And I think it's easier if I show like an actual example, and you guys will have a chance to actually write your own class as well. So this is an example of creating a dog class. So I'll just run through the code step, like sort of line by line, so you see how it works. This is how you introduce a new class. So you go class and then the name of your class. And whenever we make names of classes, we always start with a capital letter. So capital D for dog. And this block right here, this is the initializer block. So it's this thing like underscore underscore init underscore underscore. This is like the initializer method. And this is how we, usually you would do it for like basically any class that you write, but this is how we introduce attributes. So once we've defined this initializer method, we want to insert whatever parameters, like whatever parameters we insert here, those are our attributes. So we have name, we have breed, we have age, and color. So an attribute is something that every instance of your class has. So by writing it here, every dog I create later will have all of these properties that you can call on. So the name, the breed, the age, and the color. And we just write, like we always need to write self here. All the others are just your attributes. And then self.name like equals name. This is how like the object's able to refer to itself. But you can just memorize it as like a bit of syntax that you always need to include when you're sort of introducing these attributes. Does anyone have questions on code that's up here?
Wait, so
Yeah.
the self.name, it means like when you make an instance of the class which is an object, the self.name, the name after the self is different to the name after the equals, right? So the name after the equals refers to the name in the parentheses.
Yeah. So for example, down here when I create my first like dog object, right? I'm able to go like dog1.name. If I did dog1.name, it would spit out this property, which is buddy. Yeah. So it is different. And then like say I had dog2, right? Later on, I might write down dog2.breed, and then that would spit out the breed of that dog, which is husky.
Does it just ignore the self part because like you're not how do I put it? Like when you write dog one, you know how like it puts it into the initializer and it doesn't have a self thingy, it just has new breed, age, color.
Yeah. It just ignores the self thing. So the self thing is just something like you need to include in your initializer.
So like theoretically you could say like self.birthday equals age, and when I do dog1.birthday, it should return the age, right?
Yeah.
Okay. So it's just another name, but we're just naming it the same thing again.
Yeah.
Okay.
That's right. Yeah, so that's the attributes, right? And then when it comes to methods, you have, this is how you introduce your methods. So you define it the same way as you define like a function, right? But the difference is that for your methods, these are all tied to the objects of your class. So when I do, like when I define bark, and then I just include self as well to show that this is a method, this is what I want bark to do. So it basically just says the name and it says like, this dog says wolf, right? So that means that later on when I call bark, so I might do dog1.bark, and I need to add those brackets in at the end. So for the attributes, when you call them, you don't need to have brackets. But for any method you call, there will always be brackets at the end when you're calling it, right? So dog1 dot bark brackets, and then that will print out this into the terminal. And same thing with describe. So for like you write this describe method, and then it'll print out like the name of the age, the color, and the breed. So all of these attributes that we wanted. And that's sort of like your crash course in how you write the methods. And this is how you actually create the objects. So whenever you create an object, you specify the name of that object, right? And then you use dog, so with a capital D again. And then in the parentheses, you need to include all of these parameters, except for class. There's also an option to sort of like set default values for any one of these, but I think we'll see that later. For now, just like focus on this stuff. So anyone have questions on this? And then we'll actually hop in and get to do some ourselves. Nope? Okay. Oh yeah, so this is what happens when you actually call the method. So if I wrote down like this, dog.bark, and then brackets, dog.describe, brackets, it comes up with this into the output terminal. So that's just like sort of a look at how it actually works. And of course, this is a really simple example, but you can imagine that classes can get very, very complex, and you can have very complex methods. And like the more sort of like complex and useful they are, the better, because then you can export all of that to someone else, and they don't have to write any of that code themselves.
Wait, so when you say like libraries, how do
Yeah.
libraries link to classes? Are they just like different classes that other people created?
Yeah, so a library is like a collection of like code that someone else has written. And within that code, usually people would like write classes and stuff.
So when I do import math, right?
Yeah.
I'm actually importing a class called math.
Oh no, so you're importing the library,
Yeah.
the library maths, and within that library, there's like the person who wrote that library would have like written a bunch of classes that you can now use in your code.
So when I do math.square root, like on my end, what is that calling on, like what is that actually?
Oh, so the math, if it's math.square root, then math would be the like the object,
Yeah.
and then the square root would be like the
The
method.
method inside the object.
Yeah.
Okay.
Yeah. Okay, so you can now go to this thing. I'm gonna post it in the Discord actually because we'll have a bunch of tutorials. So just a few simple exercises. I'll give maybe like 10, 15 minutes for you guys to work through this. All right, let's come back. We still have a few more exercises to work through, so we'll try and move on. Can I get a show of hands who like completed everything? Yeah, most people. It's okay if you haven't completed everything. You can go through it like later on as well, and just ask us questions if you have any. But so now that we have an idea of like what object-oriented programming is, and I guess we have a bit of an idea of like the setup of a library, classes, and objects and everything. We're gonna look at some important libraries that will be relevant for your projects later on, and also like useful for AI and for ML in general. So the first one, so this is like, Python is one of the like very powerful languages because there's so many libraries that have been written for it. So whatever like functionality or problem you run into, like if you don't think there's like some solution, there probably is someone like out there who has encountered the same problem and created some sort of way to fix it. And you just need to find a library that allows you to do that. So this is some of the important libraries that we'll be going through. So this one's NumPy, this is Pandas, this is Matplotlib, and SciPy, PyTorch, and scikit-learn. So we're gonna have a bit more like in-depth exercises for these top 3 ones. I posted the links in the Discord already, but don't go straight there yet. We're gonna start with NumPy. So NumPy, we've already done a bit of it. So it's short for numerical Python, and it's for working with arrays. Essentially what NumPy does is it provides this high-performance multi-dimensional array object, so ND array, or n-dimensional array. And the thing about NumPy is that these arrays, although they appear very similar to your normal Python lists, they are much quicker, especially for calculations. And that's because Python's sort of objects, these arrays implement those values at a much lower level compared to Python, where you have to sort of make all of the values into like some abstract like data structure, and that takes a lot more time than what NumPy does. So I think the best way to sort of go through the basic functionality of NumPy is through this Colab tutorial, so I'll go to that. And you guys can just follow along on the screen first, and then we'll have exercises for you to do later on. So the thing about today is that we're going to go through a bit of NumPy, a bit of Pandas, and also Matplotlib, but this is like only scratching the surface. So I'm just going to go through basic functionality and hopefully set you guys up to be able to learn more once like this is over. But I'm just going to go through like the basic functions and things. So when it comes to NumPy, you need to first import it here. So usually you import it as np so that when you refer to it later on, you can just do np dot whatever. So I'll just give it a second. Yep. And these are our arrays in NumPy. So we create one by going np.array. And then within the brackets, we would put in our, within the brackets, we would put in our values for the array. And for all of these arrays, this is how you can print out the type of this object. So you can say that you can see it's a NumPy ND array. And when you print out the shape basically gives you usually the rows and then the columns. But for this rank 1 array or one-dimensional array, it will just give you the length of it. And then this is how you can index, just like an array, like that. You can also edit it the same way as list, and then just you see when you print it out, the new array is now changed. So this is how you create a rank 2 array. So notice you have 2 layers of brackets now. So once you to put the outer brackets, you have the first layer of square brackets, and then within that you have your list of different like square brackets. So those would be your rows. And now when you print this out, you can see how it appears like that. This is two-dimensional now. When you call shape, so shape again is one of those attributes, right? You can notice it's an attribute because there's no brackets after it. You can just use it like that. Now, this is what happens when you print out shape. It tells you the number of rows, and then it tells you the number of columns. And you can index the same way as you would with a 2D list. There's also a bunch of other functions that allow you to create special arrays. So this one is np.zeros. So whatever array, you just specify the shape here, so the rows and the columns. And whatever you print out will just be filled with zeros, like that. Can someone explain to me why there's dots after each zero? Yeah, it's float. So this method automatically just creates a float. So that means that it's like essentially a decimal point rather than integer. Same thing with ones, and then with full, this is what you use when you want to create an array that has is full with a certain value. So in this case, I specify first the shape of my array. So it's 2 by 2. And notice that this is within its own set of brackets. And then I do comma and I tell what value I want to fill it with. So in this case, it should be a 2 by 2 row, a 2 by 2 2 by 2 matrix of 7s. And this one is how we create our identity matrix. So if you remember, our identity matrix is just the diagonal matrix full of 0 with just the diagonal filled with 1s. So np.I, and then can someone tell me why we only have one number here instead of like the shape like here? Yeah, that's right. So our identity matrix is always square, so we only need to really put in one number, and that will define our dimensions. And same thing for random. So you can also slice these matrices the same way. You would, and this is how you slice it. So you would call on whatever array you've created first, so this A. And then I want to specify what rows I want to take first. So if we remember, what happens if we just have the colon and we don't have any value before it? Yep. So it just goes all the way from the start, right? So if I want to specify what rows I want to take, by leaving the first value blank here, I'm just going to start from the first row. So this is my first row, and then this is 0, 1, 2. But remember that the last value is not inclusive, so we're only going to take these top 2, right? Then I want to specify what columns to take as well. So I'm starting with 1. So this is 0, and this is 1. Then 2 and 3, but we're not going to take 3 because it's not inclusive. So now we're going to take the intersection of the first 2 rows and the first and this middle 2 columns, and that's what it prints out here. So it's 2, 3, 6, 7. Does that make sense? Does anyone have questions about that?
So just to clarify, the first number is inclusive, but the second number is not.
Yeah, that's right. When you're slicing, and this applies for like your normal list as well, your first value before the colon is inclusive, whereas this one is not. Yes, and it's also important to note that when you slice an array, this is not suddenly its own sort of separate object. You have essentially just created a view into a specific part of the array. So that means when you modify that part, it will actually modify the original array. So this is an example, right? I'm going to first print out, so 0, 1 of A. So this is A up here, and 0, 1 would be this 2 right here. When I change the 2 in my B array, which is just my view of the original array, to 77, and I print out the original, it comes up with that 77. So I've actually modified the original array. Yep, and these are just some ways of, so I'm just going to create this array first. these are some other ways of creating views. So if I slice and just specify that I want to take the first column, the first row, then I'm going to end up taking this. So because we're zero index, I'm going to take the middle row. And for the columns, since I left it blank, it's going to take all of the columns. So this whole middle row. And these are just like some other ways of doing the same thing, of taking the middle row. But notice that when I mixed, so when I'm slicing, right, and I take, when I'm slicing, I always use this colon. But when I'm doing integer, I just take this, I just put in a value. So it might be 0, the 0th element, or the first element, or the second element. By mixing this integer type like indexing with the slicing, I actually reduce the dimension of the slice. So when I take it out now, you can see that this first method doesn't have that double set of brackets. It's now one-dimensional. Whereas these two are still two-dimensional in the way that they just have that one row, but they're still a two-dimensional object. So now if I were to call shape, remember when I call shape on a one-dimensional object, it just tells me the length. That's what happens. Whereas when I call shape on these two-dimensional objects, it tells me the row, and then it tells me the column as well. Anyone have questions on that one? Nope, okay. And then this is the same thing, but using the columns instead of the rows. You can also specify what data type you want the array to be filled with, just with this argument after. So dtype equals, and then you specify the data type. And you can also perform sort of any maths using these arrays as well. So I've created two sort of arrays here. There's x and there's y, and then I can just add them. These are equivalent expressions. You can either just x plus y, or you can do np.add, and they would come up with the same result here. And the same thing works for subtraction, and for multiplication, and for division as well, and also for square root. Later on, we'll be seeing how it's really important that we're able to use dot product and use our matrix multiplication. And this is how we can do it within NumPy. So I've just created 4 different arrays here. And to create to get this dot product, right? You can either take one array and then dot it, and then specify which array you want to dot product it with. Or you could do np dot, and then take the two sort of vectors or matrices that you want to dot product, and they come up with the same thing. Yeah. At symbol is just another way to do it as well. And then these are just more examples of doing the same thing. Yep. And this is how you create a transpose as well. So we remember our transpose matrix is just our matrix that is flipped across the diagonal. So we just specify that using, so we have x. X is one of our arrays. We go x dot t, and that becomes our transpose. Yeah. There's also some other stuff on broadcasting here, but I won't cover it now because it's a bit out of scope. But hopefully you guys can just play around with some of these functions first. So within the Discord, I also sent this problem set. So you guys can try to work through that as well on your own. And then also refer back to this if you need. Yeah, so we'll spend the next 20 minutes or something doing that. Okay, let's move on now. So actually, before we go, there's one more slide I had on the different symbols for operators. For dot product and matrix multiplication, etc. So we have our 3 different similar-ish sounding operations. So we have the dot product, which, just as a reminder, it creates a scalar product, right? Once you run it. And matrix multiplication is when it's like what James has been going through, where it's sort of a bit more complicated, where you have to rotate your second matrix, and then once you multiply them, that becomes the first term of your new matrix. Element-wise is where the first element multiplies with the first element of the second matrix, etc. This is the sort of symbols that you would use for it in NumPy, and these are the built-in NumPy functions as well. Just you can see there's at the at symbol on both the dot product and the matrix multiplication. So this operator is quite useful, and it's probably the main one that you use, but it adapts to the dimension of your arguments. So for example, if you have two 1D vectors and you try to at them, so like A at B, then it will come up with your dot product. So that's just the one number. But if you have two rank 2 / two-dimensional arrays and you do the at between them, then it'll come up with the matrix multiplication, and you can only get the dot product if you flatten them. So there's another sort of method called flatten. You go like a dot flatten brackets, and that will turn it into like a one-dimensional thing. And then using that flattened version, then you can dot product it. So just like keep in mind like these different operators and the difference between these operations. Okay, we'll take a look at pandas now. Pandas is probably something you'll use tomorrow as well with Qua. This library is really powerful for data preparation and analysis, and it's going to be very widely used for you because later on acquiring data, pre-processing data, that's going to be sort of the main part before training your model. So the two main classes that pandas sort of introduces is series, which is a one-dimensional array. So you can imagine a series as like a one column from an Excel spreadsheet. And then there's also data frame. So that's like the whole spreadsheet, two-dimensional structure. And again, we have some like tutorials on this. I will just run through that quickly before lunch. So this is how you import pandas. Import it as PD. And this is how you create a series. So right here I have a list, a normal Python list, which I've named data. And once I insert it into this series call here, then this is what it prints out. So this is my data. This is what I was saying when I said it was like a column in an Excel spreadsheet. You have all your data down in the column, and you also have an index for each one. And there's options to change like the indices and everything as well. And that just tells me my data type as well. This is how you create a data frame. So I start with a dictionary here. So the dictionary has 3 different rows, and if I want to turn it into a data frame, I use this very similar looking function here. And this is what I come up with. Again, it has the same thing, so it's all the headers. So the keys from the dictionary become your headers, all the values get inserted into the spreadsheet, and you still have the indices going down the side. So just as a bit of a demo, I'm just going to use a data set that I got from Kaggle. So if you don't know about Kaggle, well, I'm sure you guys should know because we recommended that you do the course. But they also offer a lot of data sets. So any of these you can click on and you can use to train your own model. So I just downloaded one of them, and I have it here, I believe. Or maybe not. Insurance. Okay. So now that I've uploaded it onto my Colab, I can open it using my commands and things. So CSV_data is equal to my file, and then I can read that data out. So, oh, how's it not work? CSV, oh, yep, that. Okay, so if I print it out, then it might take a while. Yeah, it's a very long set. So you can see it's 1,337 rows, and they haven't displayed the whole thing, but they're just showing me like the summary version. And this, actually what the data set shows is it's a bunch of patient data. So it includes their age, their sex, their BMI, and it's just like showing how much they were charged as well by medical insurance. Yeah. So I don't know like where this was, like what country this is taken from as well, but yeah. But we're gonna see what like cool stuff we can do with it, right? We haven't gone through matplotlib yet, but you can use matplotlib to plot all of this data. So this is, I've chosen to plot the age versus the, like, how much they were charged. And you can see, like, I don't know where this data was taken from, but there's like very clear difference here. So if you're older, you're charged like a lot more than, than if you're younger. So this is just an illustration of some of the things you can do with all these libraries. And the 3 libraries that we're going through this morning, the cool thing is that they all sort of integrate together. It's very easy to use them, like to work with one another. And then once you have all this data as well, and you've pre-processed it, it's easy to turn your data frame back into a CSV file. So this is the command to do so. And then now if I look in here, I have an output file. And if I click on the output file, it should have all of my data here. These are some options you have to just view parts of your data. So there's .head, which shows the first 5 rows. There's .info, which gives you a bit of a summary. And there's .describe, which gives you like key statistics for your data. So things like the mean, like the standard deviation, and your quartile ranges. You access your data the same way using indices, or you can also use like the labels of your data. So in my data, I have things like name. Oh, not this imported data, but the original data that I made up here. So there's like name, age, city, things like that. I can reference the data using those same things to print them out. Same thing with indexes. You can also add columns. So this is all about like pre-processing. You can add columns like this. So my new data looks like this here with the new column here. Same thing to remove it. Now it's gone. You can filter it. Check for missing values. Fill in those missing values as well with whatever you would like. And then this is another example of matplotlib to create a bar graph for my data. So I won't go through it in too much depth, but this all will be made available for you, so you can go around and play with it. And I think Kaggle has a really good course as well on pandas, so you guys can check this one out as well. But yeah, so now that we're done with pandas, maybe we'll skip the Kaggle problems for now because we're nearly at lunchtime. I'll just do a quick overview of matplotlib as well. So we saw some of the applications of it already in that previous collab, but it works really well with your NumPy and your pandas. And this is a short tutorial I made. So this is also similar to MATLAB. I've never used MATLAB before, but they tell me that it's similar to MATLAB, yeah. Okay. So we'll give it a bit to connect. Yep. Don't worry about this one too much. So this is how you import it. Don't worry about this too much. So I think this is just so like you display your graphs under the cells. But the most important function for matplotlib is your plot function. And this will allow you to plot your 2D data. So here we use that command that James talked about before. So the function arange. And what arange does is you specify your two first parameters, and that's your sort of lower bound and your upper bound. And arange will create evenly spaced, like a list of evenly spaced values between those two bounds. It'll create an array, actually, a NumPy array. And you can also specify the step. So by default, if you were to do like 0 to 10 and nothing else, then it would just count up by 1. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if you wanted to specify like count by 2s, then you would do that after those two bounds. So in this case, I've specified 0.1. So every like value within the array will be counting up by 0.1. And then I have my y values here, and it's easy to just plot it. So I specify my x values, my y values, and this is the output, like that. And this is sort of like a similar thing, but let's say your data was not split into a list of your x values and a list of your y values, but you just had one big list, and each element within your list was like your x and y value pair. So if you wanted to plot something like that, the way you could do it is using this zip function, and then it would unzip it and split it into two different arrays. And you can also create sort of subplots. So this is when you have a figure with two different graphs in the one thing. I'll leave all of this for you to take a look at after as well. And then you can also create bars, scatter plots, histograms, etc. And obviously, you need to be able to sort of save all of this stuff to make it useful. So this is like the code that you use to save it as well, save fig. So each one of these figures, you notice when I write, for example, plots histogram, or I write, like I want to edit the title and everything. The way that matplotlib knows which figure I'm referring to is just the last active one. So the previous one that was active is this one right here. So when I run these commands, yeah, this one here. So if I run the command, it will apply on the last active one. If I wanted to sort of refer to one that I had done like previously, I want to name it so that I can refer to it later. And we name it just like this. So plot.figure1. So this is figure 1, and this is the name that I've given it. Yeah, and then you just save it here, and by running this, it saved the two figures to my computer. Yeah. So that's all for matplotlib. And just some other libraries that will be important for later as well. We have SciPy. PyTorch is something we'll go through a lot next week. So this is one of the most popular libraries for ML and for deep learning. And I think we'll have a whole day dedicated to PyTorch, so we'll get pretty comfortable with that. And then there's also scikit-learn, which is sometimes used for data mining and for data analysis and machine learning as well. We'll take a bit of a look at that next week as well. Yeah, but that's everything for now. And then I think we can break for lunch and come back at 1:30. Is that right?
Yeah, like maybe 12:55. 12:55. Oh no,
12:50.
1:25.
1:25. Okay, yeah, 1:25. Okay. See you guys after lunch.